Hello, I am V. Ragasuma. Welcome to chemistry class. Today's class we are going to explain you about we are going to see about the spectrophotometry. So generally the introduction, visible light is a form of energy and it is generally it has two theories, wave theory, corpuscular theory. Okay, some properties were explained on the wave theory and the other properties in the corpuscular theory. Wave theory, it is mostly used in the spectrophotometry. Okay, so visible light, a form of energy. So in that two theories, the wave theory, it is most useful in the spectrophotometry. What the wave theory tells is the propagation of light by light waves involves both electric and magnetic forces. And commonly light radiation, it is referred as the electromagnetic radiation. It is referred as the electromagnetic radiation. You can see the magnetic field and the electrical field, both the components we can see. So the characteristics of this light is the wavelength, wave number, frequency, velocity. These are the characteristics. And the spectroscopy, it is having both the absorption and the emission spectroscopy. Now we'll see spectrophotometry. The compounds absorb light radiation of the specific wavelength. The compounds absorb light radiation of specific wavelength. The light, whatever is absorbed by the sample, it is directly proportional to concentration of the sample. As the concentration increases, absorption increases exponentially. Okay. So, what the light that is absorbed by the sample is proportional to the concentration. As the concentration increases, even the absorption increases exponentially. Here you can see the concentration on the y-axis, absorbance on the concentration on the x-axis and absorbance on the y-axis. The standard curve with the imaginary data we have drawn. As this concentration is increasing, you can see even the absorbance is increasing. If the concentration is increasing, the absorbance is also increasing. And both of them are directly proportional. As the concentration increases, you can see the graph, how it's increasing. As concentration is increasing, even the absorbance is increasing. So this is the main principle in the spectrophotometry. So a method in which absorbance or the transmission property, it's a method in which absorption or transmission property of a material quantitatively measured as a function of wavelength. Yet the basic principle behind this method is that each compound absorbs or transmits light over a certain range of wavelength. Okay. So each component absorbs and transmits light over a certain range of the wavelength. In this electromagnetic radiation, you are having different regions. Cosmic rays, gamma rays, X-rays, ultraviolet rays, visible rays, infrared rays, microwave rays, radar rays, television rays, NMR rays, radio rays, and current rays. So the different rays we have seen for the electromagnetic spectrum. When a light or electromagnetic radiation of intensity I0 passes through an optical medium or a solution, part of the radiation is absorbed IA by the substances and a part is transmitted IT and a small part remaining, that is IR. So these three phenomena occur when the light passes through a solution. Intensity of the incident radiation, absorbed radiation, transmitted radiation light, and the reflected light are related to this. I0 is equal to IA plus IR plus IT. I have told you about the line. Now, spectrophotometer, it is an instrument. It is an instrument that measures the amount of photons absorbed by a sample after it is passed through its solution. With the spectrophotometer, the amount of known chemical substance can be determined by measuring the absorbance. So, spectrophotometer, it measures the amount of photons absorbed by the sample on passing through the solution. The amount of the chemical substance to be determined is measured by the absorbance. Very simple. Okay. So we need to know the concentration using the spectrophotometer. How will the concentration be known? Amount will be known just by measuring the absorbance. How much ever it is absorbing the photons, that is the amount, that is the concentration. The concentration is directly proportional to the absorbance. Now we'll see Beer-Lambert's law. First, Beer's law we'll see, and later we'll see the Lambert's law. So, on combining together, Beer-Lambert law states that the absorbance of the light by a material in a solution, it is directly proportional to its concentration in that solution. A is equal to extinction molar absorptivity into length of the solution into concentration. Absorbance is proportional to length and concentration. So we'll see in detail about the Beer law and the Lambert law. Lambert's law, the proportion of the light that is absorbed by a medium is independent of the intensity of the incident radiation. A sample, it absorbs 75% and 25% is transmitted. 75% of the light will always absorb 75% of the light, and no matter and the strength of the light source. So it is expressed as I by I0 is equal to T. I is the transmitted light, T is the transmittance, I0 is the intensity of the light. So this allows different spectrophotometers with different light sources to produce comparable readings independent of the power of the light source. So Lambert, what he explains is, when the monochromatic light passes through the transparent medium, the rate of decrease in intensity with the thickness of the medium is proportional to the intensity of light. So when the monochromatic light passes through a transparent medium, the rate of decrease in intensity with the thickness of medium is proportional to the intensity of light. This is equivalent to the stating that intensity of the transmitted light decreases exponentially as thickness of absorbing medium increases arithmetically. So minus di by dt is proportional to I, minus di by dt is equal to ki. So ln I0 by IT is equal to kt, or IT is equal to I0 into e power minus kt. Okay, so now we'll see about the Beer's law. The absorbance of the light, it is proportional to both the concentration. Here the absorbance of light is proportional to the length of the substance. So the absorbance of light is proportional to both the concentration of the absorbing medium and the thickness of the medium. So in the spectrophotometric, thickness of the medium is called path length. Okay, so the path length, it is measured in centimeters because of the standard photometer uses cubed 1 centimeter. So thickness of the medium, Lambert's law. Simple way, just remember Lambert's law. When the monochromatic light passes through transparent medium, decrease in intensity with the thickness of medium is proportional to the intensity of light. Intensity of light, decrease in intensity of light is due to thickness of the medium. That's it. When monochromatic light, what is monochromatic light? The light which is having only one direction is called monochromatic light. So when monochromatic light passes through the medium, it passes through the medium. Whatever is transmitted, the transmittance is decreasing. Intensity of the light after transmitting, intensity of the light, the decrease in the intensity of the light after passing is proportional to the thickness of the medium. The decrease in the intensity of the light after passing through the thickness of the medium is proportional to the thickness of the medium. That is Lambert's law. So the intensity of transmitted light decreases exponentially as the absorbing medium, thickness absorbing medium increases. So this is Lambert's law. Now we'll see about the Beer's law. Beer's law, it's nothing but the same, that absorbance of the light is proportional to the length of the medium, length of the thickness of the medium, length and the thickness of the medium. So here Lambert's law, what it explains is transmitted light decreases due to thickness of the medium increases. Similarly, transmitted light decreases due to increase in concentration of the absorbing medium. That is Beer's law. Lambert's law explains about the thickness of the medium. Beer's law explains about the path length of the medium. So this is the way, on combining both of them, we get Beer-Lambert's law. Okay, so Lambert about the length and the Beer. Here, both of them combining, one is length and one is the one is the thickness. So intensity of the monochromatic light decreases exponentially as concentration of the absorbing medium increases. That is Beer's law. Okay? Intensity of the monochromatic light decreases exponentially as concentration of absorbing solution increases. Okay, so this is the path length and this is the concentration. You can see incident light, cuvette, transmitted light. Absorbance is directly proportional to concentration of the solution of the sample used in the experiment. Absorbance, it is directly proportional to concentration of the solution of the sample used in the experiment. A is proportional to C. A is proportional to L. Beer's law, Lambert's law. A is proportional to C, Beer's law. A is proportional to L. Absorbance, concentration, length. On combining the two relations, you get A is proportional to C into L. So the proportionality is taken out and it is converted into the equation including the constant. Molar absorptivity. A is equal to E L into C. Now what is transmittance? The amount of monochromatic light absorbed by a sample is determined by combining the intensity of the incident light I0, transmitted light I. Transmittance. The ratio of the intensity of the transmitted light I to the intensity of the incident light I0 is called transmittance. This is the absorbing medium, absorbing sample of the solution, path length, I0 and I. Incident, transmitted radiation. This is the incident light and this is the transmitted light. This is the sample and this is the sample. And this is the complete path length. Okay. So this is the incident light and this is the transmitted light. I0 by here, transmittance is equal to I by I0. Transmitted light by incident light. Percent of the transmittance is nothing but percent you have to express in 100 with respect to 100. I by I0 into 100. So the ratio of I by I0, transmitted light by incident light, is transmittance. So transmitted light by incident light is transmittance. Percent transmittance is I by I0 into 100. Next, absorbance. From the transmittance or percent transmittance, we can calculate from transmittance or percent transmittance, we can calculate the quantity as absorbance. So absorbance is the amount of light absorbed by the sample. Okay. From transmittance or percent transmittance, we can calculate the quantity of the absorbance. Absorbance is the amount of light absorbed by sample. Absorbance is logarithmic function of t and it is expressed as absorbance is equal to log 10 1 by t. So 1 by t can be given by minus log 10 into t. This is equal to log 10 of I by I0. In the simple way, using transmittance, we can calculate the absorbance. It is the amount of light absorbed by the sample. That is absorbance. Amount of light absorbed by the sample is absorbance. So it is the logarithmic function of t. Absorbance is equal to log 10 of 1 by t. Absorbance is equal to minus log 10 t. Again, t is I by I0. Okay, so we have seen the principle. What is spectrophotometry? Principle behind that one. Lambert's law, Beer's law, and what is transmittance, what is absorbance. So now we'll see the instrumentation. Spectrophotometer is classified into two different types. Single beam and double beam spectrophotometer. The spectrometer, single beam we are having, that is the first one. So Beer's law employed in the quantitative analysis of the chemical substances. If the solution is colored, the instrument employed in such accurate colorimeter or photometric analysis called photometer. Instrument employed in accurate colorimetric and photometric analysis is called spectrophotometer. A spectrophotometer is a filter photoelectric photometer. Previously, what they used to do is refined filter photoelectric photometer. It's nothing but spectrophotometer. A spectrophotometer, it permits the use of continuous variable monochromatic bands of light. Variable and near monochromatic bands of light. The essential parts of the spectrophotometer are source, a radiant energy source, monochromator, prism or grating, glass or silica cells, that is nothing but cuvettes, and device to measure the beam of radiant energy which is passing through the solution of the solvent. To measure the intensity of the incident light, the sample must be removed so that reference can be placed in each time. It is less complicated and less expensive. Always you need to take a reference or a standard for each time. So for each measurement of the sample, you need to take the reference. Then your sample. You have to keep changing at every time. The type of the spectrophotometer, it is expensive and less expensive and less complicated. Light sources in the instrumentation, the light source, monochromator, sample, light detector, computer, computer, or a chart to display the results. Okay, here light source, monochromator, sample, detector, and display. Now we'll see this instrumentation in detail. Now, a small fraction of the radiation, a small fraction of the radiation, it is emitting from the source. It is split out by the beam splitter inside, it's not shown, and it is used for the comparison of the beam to compensate variations in lamp. And the two radiance they go through, and here, as you can see, a small fraction of the radiation that is emitting from the source, it is split off by beam splitter, and it is used as comparison beam to compensate variations of in light output as well as line voltage fluctuations and the electronic instability. Two radiation sources are used here: quartz and a halogen lamp for visible range, deuterium for the UV range. Monochromator is gray. Detector is the photomultiplier tube. Photomultiplier tube. Yeah, the monochromator is gray. Okay, light source comes here, goes into the monochromator, and then it comes to the sample. You can take first reference, then change it to the sample. And absorbance, it is noted. Transmittance and absorbance are noted. Okay, I by I0, both of them are noted, and thereby absorbance is known. Depending on the length and the concentration of the sample, the transmittance will take place. The absorbance and the transmittance will take place. Now it comes to the detector. And how much ever is absorbed and the remaining transmitted is detected. Thereby we can find out the absorbance, absorbed light. So the depending on the transmittance, we can find out the absorbance. And depending upon the absorbance, we find the concentration of the sample. Because it is dependent on the concentration of the length. It comes to the display. Now coming to the double beam spectrophotometer. This double beam spectrophotometer, in this time, it reaches the sample, the light source is split into two beams. From these, one passes to the sample and the one passes to the reference. Okay. Yes, you can see reaches the sample in this type. Here, double beam. Beam, it is double. One comes to the sample and the other one to the source. One to the sample and the other one to the source. Okay, from the source it's coming to the sample and the reference. Two beams, one to the reference, one to the sample. Okay, so light source, here it comes to the monochromator. You can see, and from monochromator here it is splitting. I told you. light, it's split off the beam splitter, and it can be used for the comparison beam to compensate for the variations in the. So here the light source, it comes to the monochromator. After that, it is split off, the beam is split off, and then one goes to the reference and one goes to the sample. Yeah, that is the reason you call it as double beam. Okay, rotating mirror and the motor. Here it splits two, one to the reference and one to the sample. And from sample it comes out, and the other one also comes out from the reference. Both of them are noted. Here the transmitted mirror. Using this, the detector will detect and compare the sample with the reference, and thereby it passes on to the display. Okay, so this is the way it functions. I'm repeating, in this instrument double beam monochromator light, it is split off or chopped off into two components, usually equal radiant power. One beam, one beam passes here. It passes here. One beam passes through the sample, the other one through the reference, and usually equal radiant power is used. One beam passes through one, and the other one is through the blank or the reference solution. However, the radiant power in the reference beam varies with the source of energy. And if the output of the reference beam is kept constant, then the transmittance of the sample solution can be recorded directly as the output of the sample. There are several ways to keep the reference output constant. They are regulation of the photodetector sensitivity, controlling the monochromator slit width, positioning an optical wedge in the radiation path. So light monochromator slit, and two, it is getting split at double beam, then detected and amplified and recorded. Okay, based on the wavelength of the light used, it is classified into different types: visible spectrometer, UV spectrometer, IR spectrometer. Here, visible range, it is from 400 to 700 nanometers, electromagnetic radiation spectrum. Visible spectrophotometer varies in the accuracy, plastic and glass cuvettes, and it can be used for visible light spectroscopy. UV spectrometer, it uses light over the UV range. It is from 180 to 400 nanometers. And UV spectroscopy, it is used for fluids and even solids. Okay, plastic and the glass cuvettes can be used for visible light. This UV spectrometer, it uses light over the UV range. It is from 180 to 400. Where here the visible range, it is from 400 to 700 nanometers. This visible range, it is from 400 to 700 nanometers visible range. So this range is used in the spectrophotometer, and it varies accuracy. And here in the UV spectrometer, it uses the light over the range of the UV. It is from 180 to 400 nanometers. It is used for the fluids and even the solids. Cuvettes only made of quartz and used for placing the samples. Cuvettes you're made of the quartz and used for the placing the samples. Next, the IR spectrophotometer. Visible spectrophotometer we have seen. UV spectrophotometer we have seen, and IR spectrophotometer. Here, the range of the light will be changing. For visible spectrophotometer, the visible range is used. For UV spectrometer, UV range is used. And for IR spectrophotometer, it uses over the IR range. It is from 700 to 15,000 nanometers of the electromagnetic spectrum. Depending upon the light range, we call the spectrophotometer. Visible spectrophotometer, UV, IR. Here, the mechanism also we have seen. It is generally two devices, spectrometer and the photometer. A device that produces typically disperse and the measure of the light. Photometer, it indicates the photoelectric detector and that measures the light. It consists of the light source, collimator, monochromator, wavelength selector. The photometer detects the light absorbed by the sample. Photometer detects the light that is absorbed by the sample. As the light from this slit is passed through the solution, and then it sends the signal to the galvanometer or display, digital display. Okay, so light source, collimator, monochromator, wavelength selector. So light source, it produces different wavelengths of the light. Collimator transmits the beam of light. Monochromator splits the light into components of different wavelengths. Wavelength selector transmits only the desired wavelength. It is the name itself will indicate you wavelength selector. Photometer detects the light absorbed by the sample as the light from the slit is passed through the solution, and then it sends signal to the galvanometer on digital display. Here is the light source. It comes to the collimator, and from collimator it passes on to the monochromator. Again, from this prism, you can see the monochromator from this prism. This monochromatic light again is split into different regions, visible region you are able to observe. And this light, visible region light, as it's coming out, monochromator light, monochromator, you get the monochromatic light. Light which is passing in one direction. Okay, light source, collimator, and this is the monochromator where it lets the different focusing in one direction, and it passes on to the sample, and the sample it goes on to the detector. After that it is detected and the digital display of the meter you can see. And now we'll see the absorption spectrum, how it is of different regions. Absorption spectrum, the spectrum of electromagnetic radiation transmitted through the substance. It shows the dark lines or the bands due to absorption at specific lengths. Due to absorption at, here you can see the a spectrum of the electromagnetic radiation. It is transmitted through the substance. Dark lines and bands due to absorption at specific wavelengths. Yeah, the wavelengths 400 you can see and 700 visible region. Generally, I'm going to explain you the different regions. Ultraviolet region 150 to 400 nanometers. Not shown here. This is the visible region only shown for us. Ultraviolet region from 150 to 400, where the molecules give the spectrum using this pi and n electrons and sigma electrons. Visible region, it is 400 to 800 nanometers. There also you get the spectrum based on the molecules containing pi and the sigma n electrons. IR region 400 to 4000 nanometers. Microwave from 4000 to 10,000. Radio frequency from above 10,000. So these are the regions, and the visible region it is varying from 400 to 700. So we have seen the double meter spectrophotometer and that types. Spectrophotometer, again it is split into two devices, that is spectrometer and the photometer. And again the spectrometer, the different components we have seen, how they are coming out. And the photometer, how it is detecting the light, we have seen in the splitting manner. Okay, so the spectrometer, two This spectrophotometer divided into two types: spectrometer, photometer. Spectrometer, here dispersion and all the light you can see, and here it measures the light. Photometer measures and this gives the dispersion of it. Spectrometer, dispersion of light. Photometer, measuring of that light. In the spectrometer, the components light source, collimator, monochromator, and wavelength. Till that, it is spectrometer. Yeah, light source, collimator, monochromator. Light source, collimator, monochromator, wavelength. Depending here the wavelength, different wavelengths, the required wavelength is selected by the wavelength selector. Okay, so this is spectrophotometer, and this part it is the photometer. This is spectrometer, and this part is the photometer. Light source, collimator, monochromator, wavelength selector. And now from here, the photometer, here whatever photometer is nothing but it detects the light, here detection. After coming to the sample, wavelength selector selects the wavelength, goes through the sample. And from here it is photometer. This photometer it detects which type of, how the sample is absorbing the light and how it's passing. And thereby it gives signal to the display. Okay, so spectrophotometer to divide the spectrometer and the photometer. How it is functioning we have seen. And the absorption spectrum also I have explained. Now we'll see the applications of the, we'll go for the applications of the spectrophotometer, B. Lambert's law, spectrophotometer. Yeah, quantitative analysis we can do, concentration measurement. You can detect the impurities, the kinetics can be studied, detection of the functional group you can do, molecular weight determination, concentration, detection of impurities, chemical kinetics, detection of the functional group, molecular weight determination. So I'm going to give you some of the examples. Concentration measurement, chromium in potassium dichromate, manganese and manganese sulfate, iron with thiocyanate. We'll see. In the chromium, here concentration measurements, impurities detection, we'll see some examples. First, concentration measurements. In a simple way, I'm going to give you. Small amounts of the chromium can be detected colorimetrically in the alkaline solution of the chromate. Absorbance is measured at 365 to 370 nanometers. Potassium chromate it is used as the standard solution. Chromium is generally oxidized to chromate by perchlorate. The color is intensified by ferric perchlorate, which is colorless. Okay. Absorbance is measured between 410. Calibration curves prepared for standard potassium dichromate and ferrous mixture solutions. Absorbance is measured between 410 to 480. Chromium it is detected first oxidized it, using the dichromate and the perchlorate. Dichromate solution made up to the mark and it is reduced back to the chromium by ferrous ammonium sulfate. The absorbance of the resulting solution is measured at wavelength between 410 to 800 nanometers. That is one example for the concentration measurements. And now we'll see the second example, manganese and manganese sulfate. So manganese in manganese sulfate, manganese in the oxidized state plus 2. It is oxidized to permanganic acid. The two oxidizing agents in uses are ammonium perchlorate in H3PO4 plus HNO3 mixture in presence of AgNO3. So as a catalyst, potassium periodate and the later here in the odd solution Okay, the two manganese in the oxidation status are +2. It is oxidized to manganic acid. Two oxidizing agents are ammonium perchlorate in H3PO4 and HNO3 mixture in presence of AgNO3 as the catalyst. Potassium periodate here in the hot solution HNO3 or H2SO4. Periodate oxidizes NNSO4 quantitatively to KMNO. The oxidized solution it is made up to the mark and the absorbance of the color is measured at 545 nanometers. A calibration curve it is constructed using the standard KMNO4 solution. Okay, some of the just simple examples were given. Chromium in potassium dichromate, manganese and manganese sulfate, you can do. Similarly, iron we can estimate using the thiocyanate. There also ferric ion reacts with ferric ion. It reacts with thiocyanate, KCNS, gives series of intensely red colored compounds which remain in the true solution. And the formula of the red compound is written. Okay, FuCNS, a low concentration of KCNS, yeah, at 0.1 KCNS concentration. At very high concentration of KCNS, it is FuCNS. In the colorimeter determination, excess of KCNS is added. Strong acids like HCl, HNO3 of the concentrations here they prevent the hydrolysis of the Fe plus. So H2SO4 is not used because sulfate ions again form complexes with Fe plus. Here the color is measured at 480 nanometers. Standard iron solution is used and the process is repeated for the construction of the calibration curve. Okay. So the third one, the chromium in the potassium dichromate, manganese in the manganese sulfate. And the third application in the concentration measurements is determination of the iron. So determination, you can even see the purity of the steel. All these can be measured spectrophotometrical. So determination of the iron with the thiocyanate I have told you. It reacts with thiocyanate, gives a solution. Okay. Now this using the colorimetric determination, excess of KCNS addition, strong acids HCl, HNO3 addition to prevent the hydrolysis of Fe plus 3. The color is measured at the 480 nanometers. Standard iron solution is used and repeated the procedure for the calibration. In this way, you do different types here, different types of the concentration measurements we have done. So, in the similar way, you can even go for the different the steel, the purity measurements, pure detection of the purities, kinetics as a rate of the reaction can be studied. How fast a particular reaction is going on with respect to time, and detection of the functional group. So, and molecular weight determination. All such type of applications can be done for the spectrophotometry. So I hope everybody have understood today's session. I'm just giving a glance of the topics that are covered in today's class. So spectrophotometry, introduction, okay, spectrophotometry, introduction, and how it's a method in which the absorption and the transmission properties measured. Next, B. Lambert's law. What is Lambert's law? Absorbance proportional to the to the length. Reed's law. Absorbance proportional to the concentration. On combination, A is proportional to C into L. A is equal to molar absorptivity LC, length in concentration. What is transmittance? T is equal to I by I0. That ratio is transmittance. And negative, the reverse of this one is absorbance. Absorbance is equal to log 10 1 by T minus log 10 T. And in this two instrumentation, I've seen single beam, double beam. Okay. Now, yeah, in the spectrophotometer, what is spectrometer and what is photometer? We have seen. What is the absorption light, absorption spectrum? We have seen, and the applications were explained. A simple way. It's a ring of chromium in dichromate, manganese in the manganese sulfate, and iron it is determined. These are the quantitative measurements, some of the examples which were explained. So in detail, it's not explained. Iron with the thiocyanate, iron in steel using thiocyanate. Spectrophotometrically we can do. So in this way, you can go for different measurements. So different types of quantitative measurements we have seen. So I hope everybody have understood this class. Thank you everyone for listening to my class. Okay. So even the chloride extraction you can do, iron extraction, iron you can do. So such type of applications, different types of applications are there. Concentration measurements, detection of the impurities, kinetics, functional group detection, molecular weight detection. So I hope everybody have understood the class. Thank you for listening to this class.